have Andrew. Talking about corps, a core calculus of hierarchical choreographic programming.
All right. Hello. Thank you, everyone. I'm really glad to see so many people here. It's really awesome to see everybody and have this workshop. So thank you to the organizers for putting this together. I'm talking today, I'm Andrew Hirsch from the University of Buffalo, where I'm an assistant professor. And I'm talking today about CORE, a core model of choreographic programming, of hierarchical choreographic programming. And I'm going to explain what hierarchical choreographic programming is during this talk. But really, this is a talk about propositions as types. And propositions as types is one of the most powerful ideas in theoretical computer science. Not only is it an immensely powerful idea in theory, it also runs some of our most important pieces of impact, like theorem provers, Coq, Lean, Agda. And what propositions as types is, for anybody who might not know, is essentially a connection between logic and programming. It says logic and programming are exactly the same thing. There is no difference. Propositions, the formulae you prove in logic, are types that you give to programs. Proofs are those programs. And I say that, with all due respect to Fabrizio and his previous work, choreographic programming needs propositions as types. We've made really big strides in the last few years in terms of functional choreographic programming, which adds choreographic primitives to lambda calculus. And this suggests that a lot should be possible with regards to propositions as types. And moreover, I really think that propositions as types would help the choreographic community. First of all, it would really help guide the design of our languages. Think about in the session types world, how much the connections to linear logic have really helped guide how people should create new languages, new types. It would also help us be able to prove things about our choreographic programs. If we had a nice propositions as types principle between choreographic programs and some logic, we would actually be able to do a lot more proofs of our programs. And frankly, it would help us sell choreographic programming. Who doesn't get excited by propositions as types? It's really cool. So, what's missing? And in order to understand what's missing for propositions as types connection here, I'm going to compare pirouette to lambda calculus. So pirouette is, I would say, the first functional choreographic programming language. It beats out core lambda, which was concurrent work, by a couple months. So not first by much. If we look at pirouette compared to lambda calculus, there's one addition. Just one. And that's the located type. We've heard a lot about located types today. But a located type just takes a process name and a local type, right? A type of some local program that has no send and receive communications. And it packages them up into a choreographic type, something that's global to the entire system. What do we do with these local types? Well, we can introduce them by having located expressions, run this local program at this location. We can eliminate them using pattern matching let or something similar, allowing us to bind local variables and reuse them later in further local computations. And we can send and receive, the standard choreographic send and receive primitive here. In both of these, C1 has a located type. So this is something that's going to compute to some value on some location that can then be sent on or bound to this local variable. And so the thing that we really need in order to get this propositions as types connection is a logical version of a located type. And, well, we actually heard about the solution earlier today. It's modal types. And modal types are really brilliant for this sort of thing. And frankly, if you look at choreographic programming, functional choreographic programming especially, and you know modal logic, this is pretty clear, but there's a problem. What modalities do you use? There's a lot of modalities in the world. Modal programming is super, super powerful. For instance, you could have epistemic logics, conditional logics, deontic logics. What do you use? And what I'm using in this work, and the thesis of this work, is that located types act like what are called doxastic modalities. And doxastic is just the fancy philosopher word for belief. So these are modalities of belief. And we're going to write A believes phi instead of box A phi because I prefer believes. And in fact, I'm going to be even better. I'm going to draw pictures. I'm going to have Alice here believing phi to represent A believes phi. So if you see a lot of that, that's what it means. And there's a core thing that can happen in doxastic logics, which are nested beliefs. So if you have Bob here, he can have beliefs about Alice. For instance, here, Bob believes that Alice believes phi, or believes not phi, excuse me. And in fact, Bob can't just, it's not just the case that Bob can have beliefs about Alice, but Bob can be wrong about his beliefs. So for instance, Alice actually believes phi, and that's okay. And this is really fundamental to doxastic logic. First of all, nested modalities are just super important to all modal logics. And the fact that these beliefs can be wrong is really what allows us to have doxastic rather than epistemic logic, right? An epistemic logic is a logic of knowledge. If Bob was always right about his beliefs, we would be arguing about things that he knows, not just things that he happens to believe. But this is a big mismatch with pirouette. After all, in pirouette, the local types are local. They come from a completely different language. So you can't start nesting things inside of this. So pirouette just can't express nested beliefs. And well, if you know the literature on functional choreographic programming, you might ask, well, can core lambda just come to the rescue? After all, in core lambda, we have the same language used for local programs and for global programs. But those local programs are restricted so that they are truly local. So they don't actually solve this problem. You can imagine using polycore lambda, which is a polymorphic variant of core lambda that Fabrizio and Eva and I worked on. And this gets a lot further. You actually get something that looks a lot more like an earlier talk that we saw if you tried to take this route, I think. Although I haven't tried it, so I'm excited to hear more. But we can solve this problem by instead recognizing a phenomenon in doxastic logics, which is that nested beliefs create new agents. And think about it like this. Alice here and Bob's version of Alice have different beliefs. So they must be different agents. So somehow we have Alice and a version of Alice that lives inside Bob's head. You can think of Bob as simulating Alice. So what we need somehow is a hierarchy of agents that we can reason about and program with. Hence, hierarchical choreographic programming. And what you get is a hierarchical topology where Bob can have sub-agents, Alice. He can also have a sub-agent named Bob, that's okay. Alice can have her own sub-agents, Alice and Bob. And in fact, these can live all inside some world of ground truth. Right? You can just talk about things that are true. Nobody believes them, they're just true. And that might include the fact that Bob believes some things. And this might seem like a lot of artsy-fartsy, airy-fairy, I'm doing philosophy now, where's the computer science? But real networks have these tree-like topologies that I'm building. Right? So you might have network terms that reference an entire network, but you might also have servers, and those servers might have cores, and you might want to program each of those cores independently, but you need to know which server they're on. So realistic networks have this sort of tree-like topology. So now we get to the big question, how do we represent hierarchies? After all, we now have A.C has type A.tau, where C is a choreography, and tau is a choreographic type. And we have to somehow say, well, this is only true if C itself has type tau in some context, but what context? After all, A should only have access to their own part of the context. They shouldn't have access to what's going on Bob. So what do you do? Well, you can do some complicated proof surgery here, mess with your context and work something out. And in fact, this is exactly what pirouette does. And it works at pirouette. But it turns out once you start having these hierarchies, it turns out to be very non-compositional. So what do? It turns out there's been work on this recently. And it draws on something old from logic called Fitch-style proofs. They come from this book. And Fitch-style proofs in this setting come with a notion of modalities, which is basically a path in this hierarchy of agents. So it names some particular agent in this hierarchy. And this actually comes from some previous work I did, not at all involving choreographies, but on something called authorization logic. I wrote a logic called FLUFFLE, the flow-limited authorization first-order logic. And it's a type of doxastic logic. We call these generalized principles in there. You then modify the context. We're used to contexts mapping variables to types. And they're still going to do that. But everywhere that you map a variable to a type, you're going to write down who owns it. Where is this located? And we're going to add a new type constructor, this lock_im, that represents a restriction to im's view. Now, this might seem pretty complicated, but it has been shown in a paper that was referenced earlier today to scale all the way to dependent type theory. So we know that it's actually a very compositional way of doing things. So we can use this to fix our first mismatch, but we actually have another mismatch, which is, well, we want choreographies. So we want to be able to send data. And what sending data does is just change the modality. But doxastic logics, most of them, have no native way of changing modalities. And this is where the authorization logic comes in. So authorization logic adds one thing on top of doxastic logics, which is adds trusts. Bob trusts Alice, which they write as Alice speaks for Bob. And what this says is that whenever you know that Alice believes phi, you can use the fact that Alice speaks for Bob to derive that Bob says phi. In other words, we've just communicated along a channel. So doxastic logic, authorization logic is doxastic logic with trust and communication. And trust acts like a channel. And in fact, choreographies correspond specifically to authorization logics. So I'm currently working on a language called Core. It's named after Corps de Ballet, which is the lowest rank in American ballet. I wanted something involving ranks and dancing. I also really like the fact that I could call it Core, a core model of choreographic programming. And this is designed to reflect these hierarchical topologies while having a propositions as types relation with authorization logic. Now, what we have so far, what I've described so far, is a connection between the types of a language like Core and proofs in doxastic logic. And you might ask, is this enough? And the answer is no, for a reason that Fabrizio hinted at earlier. We've not talked about the mechanics of the logic at all. So we need some way of saying, hey, if you beta reduce over there, something happens over here. And what is that thing? Well, it comes from an idea from logic called natural deduction and sequent calculus. Proof systems can be natural deduction or sequent calculus. They're equivalent in strength. And natural deduction is what you get when you just take the typing rules of lambda calculus and view it as a logic. But sequent calculus has something special because it has this cut operation. And cut is basically just substitution. You can just say, hey, I'm allowed to substitute variables in, which everybody would like to be able to have. But sequent calculus doesn't just have cut as a rule, it actually admits cut as a rule. What does that mean? It means we have no expressive power by adding cut as a rule. In other words, we can take proofs with cuts in them and remove the cuts, finding cut-free programs. And cut-free sequent calculus proofs are normal form natural deduction proofs are normal form programs. So in other words, where normal form programs mean there's no beta residues available anymore. So in other words, beta reduction is cut elimination. And this works well for lambda calculus and logic, where we say, look, if you beta reduce, we're going to consider these to be equivalent programs. We don't accept any difference between them, really. But with communication, this is a little bit more awkward, right? If I have A sends 3 to B, I can reduce that to just B has a 3. But like, are we really willing to say that those two things are equal? This seems really awkward, right? After all, the communications are different in these two programs. And it doesn't seem to correspond to cut elimination in most authorization logics either. It seems to correspond to something a little bit different. So there's a couple ideas I have here. I told you this is a work in progress, so I'm going to tell you ideas I have, and I don't know which one's going to work out. The first idea is to separate communication reduction and beta reduction. Have them as separate things, and require normal form of communications before you start normalizing with beta reduction. And this works out really well in logic. It's what both Danny Gratzer and I do in our respective works in 2020, completely independently. We discovered this. The problem is that communications and beta reduction rely on each other. So this is fine for proof surgery, but for normalization, it's kind of awkward. We could use some notion of tracing and say, well, in order to consider them beta equal, they have to reduce with the same trace. Concurrency theory uses these sorts of ideas all the time. It really complicates some ideas in type theory, because now you want to talk about programs being equal, not just when they reduce. Another idea, communication is just pure. Yeah, those two programs are just equal. Bite the bullet. In fact, in choreographic programming, in some sense, it is just pure. It's just an operation on a particular type. You just change the modality. I'm coming more and more around to this last idea being the right one. Okay, I'm going to leave you with some conjectures. I'm currently in the process of proving that core programs are canonicalizing. I have some basic proof steps that show that core beta reduction and natural reduction normalization are the same. I also have some basic ideas about correct endpoint projection involving a tree-like topology. These are all works in progress. I'm an assistant professor trying to do this on my own, so it's slow. But to conclude, authorization logic is the correct propositions as types notion for choreographic programming. Recognizing this, though, requires hierarchical choreographies, and communication makes the story with beta equivalence much more complicated, but really interesting to work on. All right, thank you very much.
Thanks. Thanks again for your presentation, Andrew. I think we are open for one question.
So I may be misunderstanding something here, but the first thought I had when you started talking about beliefs was sort of inspired by the previous talk. I think, well, if you have an incorrect belief, could that correspond to some kind of failure?
Yeah, that's a really interesting question. I think the answer is yes, but I think in order to actually talk about that in a realistic way, you are going to have to do something more complicated than I'm doing in this work. But I think there's really interesting potential extensions of this work that would go in that direction.
Okay, thanks again for your presentation. And next up, it's Andrew.
Yes, that's right. You don't get rid of me yet.
Yes, yes, with Masquerade Information Flow Control for choreographies.
All right. For some of you, you'll have seen a version of this talk before. I apologize if that's the case and you're bored. All right. So this is work with my student, Mike. He was supposed to give the talk today, but his plane ended up getting canceled. He arrived at like 5 this morning. He is here. He'll be here all week. Please ask him questions, but today he is not feeling great after being in Philadelphia airport overnight. So he's not going to be able to make it today. Or he's going to be sitting in the back. So he's here, but yeah, feel free to ask him questions, but today maybe bring them to me. It's also work with Ethan Cicchetti of the University of Wisconsin-Madison. And this talk, just like the last talk was actually about propositions as types, this talk is really about information flow security. So I'm going to start by describing what that is. So information flow security is concerned with flows, of bad flows of information. And some of those flows are direct flows. So for instance, if I have my social security number, that might be an input to a program, and it's secret. I don't want it shared with the world. So it shouldn't be shared with the public. So if I do things like just immediately output it to the public, that's probably bad. I shouldn't do that. Yeah, this is not good. We want to avoid such things. Of course, we can be a little bit more indirect. It's still considered a direct flow. So I can have some public output variable. This is a public output. It can be shared with the public. And then I can do something like this. And I've just shared a public output with the public. That's OK, right? Nothing wrong with this. I mean, I did just put my social security number in that public variable before I did this, so maybe that wasn't such a good idea either. So this is another form of direct leak. But there's another more sneaky form, which are indirect flows, which start with the same setup. I have my social security number. It's an input. I have a public output. But now I'm going to look at the first bit of my social security number. And if it's 0, I'm going to assign the constant 0 to out. And if it's 1, I'm going to assign the constant 1 to out. Hey, I'm just assigning constant variables to public outputs. What's wrong with that? I hope people see the problem. I've just used the control flow to leak the first bit of my social security number. And I said I didn't want information about my social security number getting out to the public. Oops. So this brings us to the idea of non-interference. And non-interference just says secret inputs do not change public outputs. So if I have a graph like this, and I say I have some secret inputs and some public inputs, the secret inputs are not allowed to affect public outputs, but the public inputs are allowed to affect anything they want. And I have to draw a diagram that looks something like this, that says that the public things are allowed to influence secret things, but secret things aren't allowed to go down. Right? Public here, by the way, I'm going to include public side effects here as part of my public outputs. So no using nasty side effect tricks to try to get around this. And the way we formalize this is actually by looking at 2 runs of the program with the same public inputs. And we say, well, if I have the same public inputs, doesn't matter what the secret inputs are, I should have the same public outputs. And how do we actually enforce this? How do we make sure that my programs are non-interfering in this way? Well, how do we do anything in this world with type systems? Yay, types. And our type system looks like this. And this looks somewhat confusing. I mean, there's a lot more here than you're used to. But most of it is really just the ordinary type system. We've only added a couple of extra components. The first component we've added is this information flow label L. And L here is drawn from an arbitrary preorder. So it represents a security policy. And we say that L flows to L prime. I'm going to pronounce this flows to, this square subset symbol, means that information labeled L is allowed to influence information labeled L prime. So public flows to private, but not the other way around. We also have this program counter label. This program counter label, it's drawn from the same preorder as L. It's also an information flow label. But what it does, what its job is to track the sensitivity of the control flow. So how do we use this sort of type system to get rid of flows? Well, if you have a direct flow, you have public to secret, num public to secret to unit, and num secret. You might ask, can I use SSIN as a input to output public? And the answer, if you don't have anything here, is obviously no. They're different types. But OK, we can use our information flow for subtyping. And I still can't do anything here because the flows go in the wrong direction. So that's good. Actually, I want to not be able to do this. Obviously, same story here. I don't need anything extra. But what about for the indirect flows? What do I do? Well, this is where that program counter comes into play. Because what I can do is I can say, I'm going to start type checking in public. Because there's no constraints yet from the control flow. But when I go inside of the if, I'm going to taint my PC with the label of the thing I'm checking. So here, the label of my SSN. Why? Because at this point, my control flow can leak information about the SSN. And then we're going to say, look, you're not allowed to do a public assignment like this in a tainted context. So that gets rid of those nasty effect attacks I was talking about earlier. You can't use effects to get out of me here. So all of this works really well for single-threaded programs. There's been a lot of work on this for single-threaded programs, including distributed single-threaded programs, which I think is kind of neat. But when you get to multi-threading, things start to break. Let's see why. Let's imagine I have thread 1, and what it does is it looks at the first bit of my social security number, and it's going to check if it's 0, it's going to activate T2, and then it's going to activate T3. Otherwise, it's going to do the other way around. And when I say activate here, all I mean is we're going to send some uninteresting message and wait for a response and then throw it away. Right? So we're doing nothing interesting here in some sense. And then what threads 2 and 3 are going to do is they're going to wait for this uninteresting message. I have this activate form, which just means wait for unit, throw it away, do the thing inside the body, then send unit back. Right? And what they're going to do is they're just going to output their name to the public. But now a public observer can look at this, and by seeing the order in which these two things occur, they know the first bit of my social security number again. The big problem is that if you analyze these programs separately, this program looks like it's doing nothing interesting. I'm sending some unit messages. Who cares about unit messages? Over here, however, I have no information about the control flow that led me to this point. So I can't detect that I'm actually doing a bad thing by outputting to the public here. And this leads to an uncaught leak. So we're trying to solve this with Masquerade. Masquerade is a choreographic language. It's basically pirouette, where we've added information flow labels. That's pretty much it. And what's shocking to us is that it seems to work. We have all of the nice functional things, higher order functions, recursion, etc. I'm going to skip past this slide because I went through this slide in my last talk, and you all saw it. And the key insight here is that by putting everything in a global system, we have more powerful analysis. So now I'm going to have activates, and this is just activation from a global point of view. So this is T1 sending a message to T2, T2 doing the body, T2 sending the message back. But now, when I try to analyze this program, I know what context I was in. So I can just use my standard PC manipulation tricks to establish non-interference. Yay! Now, this works as long as the local language, remember pirouette has a local language that represents the local programs, as long as that's non-interfering. And of course, if the local language allows programs like this, all hope is lost. You're not going to be able to do anything. Our conjecture, therefore, is that, well, if you have a non-interfering, if you have well-typed local programs being non-interfering, then so is Masquerade. But what if we want to do more? What if we actually want to leak information? And you might ask, why would we want to leak information? Well, imagine that I take in a username and a guess for a password. I can look up the username's actual password in a database table. I then ask, are they the same? Is the password actually the correct password? And if they are, I allow them in. And if they're not, I don't. Non-interference says this is broken, but I say this is good security. Not bad. So what do you do? Well, you start reaching for a more subtle policy than non-interference. And in the literature, there's a myriad of declassification policies that say you're allowed to leak information, but only in a controlled way. And almost all of them compose with non-interference. What that means is if I take a policy, a program that satisfies a policy P in a non-interfering context, then the resulting program still has policy P. And that means that Masquerade should be able to preserve declassifications with an appropriate local language. And so our actual conjecture, again, this is a work in progress, so we're still working on proving this, is that if the local language has a security guarantee G, which composes with non-interference, then Masquerade, with that language as its local language, has that same guarantee G. And then we get non-interference as a corollary. Like I said, this is a work in progress. We actually have a cock model of Masquerade we've been working on. We have the syntax and type system. We have progress and preservation proofs. We're currently working on a logical relations argument to establish global non-interference. We plan to use a formal trace argument to establish non-interference after projection, which is going to be a really powerful thing, really interesting to talk about. The basic form of that is, look, if projecting the global trace gives a local trace, so we can prove that if the global trace is non-interfering, which we know it is by the logical relations argument, then the local traces, when run together, must be non-interfering. And with that, I think I have some time for questions.
Thank you very much. Are there any questions? Yep. I can go.
Thank you. Do you have any ideas on timing attacks for a password?
Timing attacks. So timing attacks are really hard to deal with in information flow. You can do them, but you end up, especially with static information flow control, where I'm making sure that this program at compile time is secure. Anything that mitigates timing attacks is really, really restrictive. This is still really useful in like cryptographic settings, and people do this with there's checkers for cryptographic constant time programming, for instance. We don't want to deal with it here because nobody wants to deal with network and timing.
Oh, sorry.
Oh, no, now I'm going to get a hard question.
I'm not going to give you a hard question. Similar concept. Concurrent information flow languages do have notions of termination channels that are meaningful, unlike sequential ones. Mm-hmm. What is the sort of termination answer in Masquerade?
So the type system we have is currently termination insensitive because type systems that are termination sensitive are very, very restrictive. The logical relation is naturally termination sensitive. We have to do some work to break that, actually, in order to make the type system work. But it's pretty easy to give a termination-sensitive semantics to Masquerade. It's just that it's going to be more restrictive than you probably want to program in for normal reasons.
That makes sense.
More of a guess than a question. Are you embedding the entire census of all parties that exist in your security lattice?
No, the security lattice is an arbitrary preorder.
But there's no concept of revealing things to the public, so how do you know if you did something bad? Because there's no public in a choreography.
So every process we do associate with a label. So I guess in that sense we have an embedding, but it's not actually an embedding. It's not required to satisfy any of the nice properties an embedding would satisfy. We just say there is some label that this process is allowed to see, and it's not allowed to see more than that. So it's not trusted to enforce more than that label.
Yeah, thanks for the talk. Just one question. So there is a bunch of work on the pi calculus where you do non-interference, basically. And so my question is, doing this at the choreography level, does it give you any advantage? Because I could also imagine, I want to use a choreography language, but then I can project, and then I could use these kind of endpoint techniques instead.
So yeah, that's a great question. So the big advantage it gives you is the ability to do static things. So if you try to do, there is work doing stuff with the pi calculus and session types to try to do static information flow control. Stephanie Balzer and some of her team have done really excellent work here. Ferzan Dirkcan and Limon Jia, I believe, are the 3 people in that paper. Really, really amazing work. Really, really complicated to apply and really, really restrictive. So they have to say things like, once you've sent a message, you're no longer allowed to handle any data with a level below that message in order to avoid the problem that I showed in this slide earlier. And so they're able to establish static information flow in that case, but it's super restrictive. You can do more things dynamically, but then you have the problem of dynamic checks and termination leaks. So this gives you the ability to do static things without those restrictions.
Thanks again, Andrew. So we are closing the first session of CP, and we are going to lunch. But Lindsay asked me to, well, you can say that.
Yes, if you are in the session right after lunch, let's reconvene here. So the session begins at 13:40, but if you're speaking in that session, please come at 13:30 or 1:30 p.m. For those of us who don't understand 24-hour time. And then we'll do a quick AV check at that time. So come back 10 minutes early from lunch. Thanks. All right, let's thank Andrew one last time.